Now, the main thing that gets trickier as we look at more examples is just the application. So here, if every person has less than 500,000 hairs on their head, prove that in a city of more than 5 million people, there'll be at least 11 people with exactly the same number of hairs on their head. Now, the first thing to think about here is that if you got 5 million people to count how many hairs were on their head, perhaps someone would count them for them, and you could just do that instantly. Obviously, you're not going to have the same, it's not going to be evenly spread, is it? There's not going to be exactly the same number of people with 1 hair, 2 hairs, 3 hairs. You know, there'll be some numbers of hairs that are very uncommon because most people have quite a lot of hairs. Even bald people have hairs on their head. So what you're going to find is that there'll be numbers that are common that you get all the time, and there'll be other numbers that are very uncommon. But for this pigeonhole principle, what we're looking at is this word at least. We're saying, well, imagine that it's the most evenly spread distribution you could possibly have. And then if we've got a number, then we know that there's probably going to be at least that many people that have a certain number. In actual fact, there's going to be certain numbers that are really common or much more common than others. So let's get our head around it here. We have 5 million people. They are the pigeons, and they're flying into 500,000 holes. So imagine all these 5 million people have counted the number of hairs on their head, and they know their number, and they have to find a hole that has that number written on it and go and stand there and say, right, I'm in my little box. So if we divide the people up evenly, then we can say that there's going to be 10 people in each box. Now that's if they're the most spread out possible. Chances are there'll be a lot more people in some boxes, and some boxes will be empty. So if there are more than 5 million people, because remember the question actually said more than, and also we know that there's less than 500,000 hairs on the head. So you could use either fact there. I've chosen to use the more than fact. Then at least one hair number will be shared by at least 11 people. And that's because 10 wouldn't be enough to go round. If this number gets bigger or this number gets smaller, then this number has to get a little bigger than 10. This example is quite different from the others, and it forces you to think about the problem in quite a different way. How many odd numbers less than 20 must be chosen to guarantee that 2 of the chosen numbers add to 20? Now, here is where we start to get questions where it's quite unclear what the pigeons are, what the holes are, the remainders, and what in fact to do. So when you're feeling stuck, revert back to your problem-solving strategies. Can I write out the problem differently? Can I draw a diagram? Can I ask myself an easier question? Well, a natural starting point, I think, here is to start listing the odd numbers that are less than 20, because there's not very many of them. Now, if you had a question asking about all the odd numbers less than 500, I wouldn't recommend that. But perhaps listing the first set would help you start to spot a pattern and help you answer the bigger question. So my next question, these are just my thought processes here to help me solve this. How many pairs are there of these numbers that do add to 20? Well, it seems every single one of these has got a partner that when you put them together, they add to 20. So if I write those out, I can quite clearly and easily see that there's 5 pairs here that do. I can also just visualize them and know that there's 20 numbers, so half of them are odd, 10 odd numbers, and each one has a partner. So that helps me figure out quite quickly and easily that there must be 5 pairs. Now, these 5 pairs are the pigeonholes, because what we're saying is we want to guarantee that 2 of the chosen numbers add up to 20. Now, imagine what would happen here if I just picked 5 numbers. There's a chance that I'd get 2 numbers from the same pair if I was just picking out of these numbers here, randomly selecting them. If I selected any 5, sure, I might get a pair and I'd have 2 that added to 20 and go, woohoo, I did it. But I might not. I might end up plucking one of these, one of these, one of these, one of these, and one of these, and I wouldn't have any 2 numbers that add to 20. But as soon as I have to select more pigeons than there are pigeonholes, so if these are my 5 pigeonholes, if I have any more than that, 6 would do it, then it means that even if I was so unlucky that my first 5 picks were one from each set, the 6th number that I choose must be from one of these sets, and so it will have a matching pair that adds to 20. So noticing that there's 5 pairs, I literally just need to add one on, and you can show you're working there like that. Now, it might seem kind of babyish to write 5 plus 1 is 6, but if an examiner is wondering what I've done and how I've figured this out, to guarantee that I haven't just sort of guessed it, it's showing, by writing these out, I've shown my reasoning of where I got the 5. I've explained why I think it's 6 because I've added 1 to it. So, sure, I know how to do 5 plus 1 in my head to make 6. I don't need to show my working to work it out. I'm showing my working to prove what I did to get my answer.